Well, it's revolutionary for lots of reasons, and different people have different reasons they want to use it. But the main reason I'm excited about it is I want to understand how galaxies form. And Webb is essentially a time machine that will allow us to look back to the first generation of galaxies. So how far out you can look sort of depends on how the size of the mirror, how much light you can gather. And Hubble's mirror was 2.2 meters in diameter. So if I stood up, it would be a little bit bigger than me. Webb's mirror is 6.5 meters in diameter, so it's 3 times bigger. And it's so big, in fact, that it doesn't even fit in the rocket properly. So it's going to be launched all folded up. And then when it's traveled about, I think it's about 1 million miles from the Earth, the idea is the mirror will unfold like the petals of a flower. At least that's the idea.
JWST has got the largest mirror we'll ever put into space, 6.5 meters in diameter. So that's going to give us much higher precision in our spectra, and also much wider wavelength coverage. So we're going to get the spectra we're going to get are going to cover a longer wavelength coverage, which means we'll be able to detect more molecules and break some degeneracies in our spectra. So better quality of spectra and wider wavelengths in our spectra.
So I'm hoping to study active galactic nuclei. So these are active black holes in the centers of nearby galaxies. And we're going to look at some of the less luminous, less famous active galactic nuclei, because they're much more representative of what these type of systems can do in the universe, and we want to understand how they affect the galaxies that they live in.
There's a particular kind of galaxy that I want to look at. So in Cardiff, we carried out these big surveys with the Herschel Space Telescope, which is a different kind of space telescope. And we found these incredibly luminous galaxies way back, 1 billion years after the Big Bang, extremely vigorous galaxies that are hard to study except in the very long wavelengths. And Webb will actually allow us to actually see these things in galaxies in a lot more detail, really understand exactly what's happening in those galaxies.
So we're hoping to study the atmospheres of exoplanets. Specifically, I'm involved in an observation of a sub-Neptune exoplanet called K2-18b, which is a very interesting exoplanet that we know already has water, but we're going to be able to study this in much greater precision and much larger wavelength range than we had before. K2-18b is a sub-Neptune, and sub-Neptunes are a bit of a mystery. We don't know that much about them. We don't have them in our own solar system. And so it's an example, a very good example of a sub-Neptune. But as I said, it's also in the habitable zone, and that makes any planet very interesting, because then there's the possibility of liquid water.
I have 2 observing programs. One is to observe supernova. It's called Supernova 1987A. That is the explosion of massive stars happened about 34 years ago. So what we are hoping is JWST is catching how these massive explosions cause a shock across the space. So what's happened is when the stars end their lives, it's called extremely large explosion. And when this explosion happens and compresses the surrounding gas, it makes massive shocks. So when the time passes, these shocks is propelling through the space, and we are hoping we can trace what's going on with these shocks.
So the really nice thing with James Webb is obviously it's got a big mirror and it's above the atmosphere, so it can really help us see at high resolution and separate out these active galactic nuclei, which, as I said, are very small, from the centers of their galaxies. So you can separate out all the stars and things around them from the true active galactic nucleus, so you can study that in detail.
I think Webb cost about $10 billion or maybe $20 billion, so a huge amount of money. And ideally what you do is when you send something into space, there's no single point failure. There's nothing that can go wrong. Now, in the case of Webb, I think it's about 120 things. If any of those things go wrong, that $20 billion or $10 billion will have been wasted. And one of the biggest deals is the mirror unfolding, because it's obviously a moving thing, and anything that moves in space is a bit dodgy. So we hope it all goes okay. unfortunately, because it's going to be sent so far away, there's no possibility of sending astronauts up to fix it. So if it goes wrong, and that's $20 billion down the toilet.